Welcome. My name is Patrick Curran, and along with my non-fungible friend Greg Hancock, we make up Quantitude. We are a podcast dedicated to all things quantitative, ranging from the relevant to the completely irrelevant. In this week's episode, we discuss the sometimes terrifying issue of fungible weights in multiple regression and structural equation modeling, in which selecting a trivially worse criterion of fit can often lead to radical changes in the corresponding parameter estimates. Along the way, we also discuss competitive family Wordle, disambiguation, inflammability, perpitty, being nonplussed, running laps after practice, schmungible, audio eyerolls, Haystacks at sunset, hypereggs, the Spiderverse, mountain moonrises, tin cans and strings, and earthquake waller. We hope you enjoy the episode. You're a guy who loves words, right?
I love them.
And are you still doing the Wordle thing?
Yes, our whole family does it. We compete. This morning I lost.
And how does that differentiate that from any other morning? So what are some of your favorite words?
There are words that I have used previously, only to find out later that I'm an idiot and was misusing them in public. So I don't know if those are my favorite words, but I certainly have some memorable words.
I couldn't care less what some of your favorite words are. I want to hear a story about where you've misused a word.
I'll give you a little one and a bigger one. The little one is, you know the word infirm, like when someone gets older, they are infirm. I always said infirmed. I would say, yes, that person is infirmed. And Goldie had never heard me say it before. And then one time I mentioned, she looked at me like, did you say infirmed? I said, yeah, why? She goes, that's not a word. That's not a thing. I'm like, yes, it is. Of course it is. So, we look it up, and I was mortified because I played through all the people I had said that in front of, and then I felt like a complete idiot. So that's a small one. A bigger one, I was looking up something statistical, and it was a pretty basic idea. It was a number of years ago, and I just wanted to get a good description of it. So I got on Wikipedia. I got on early Wikipedia. And I typed in, I don't remember what the statistical concept was, and the page popped up, and it had the title of what I was looking for, but there wasn't anything on the page except one word, disambiguation. And I looked at that, and I thought, hell yes, that is exactly what it is. It is disambiguation. That is the perfect description of what we do. Oh my God, Wikipedia is amazing. And I was describing some phenomenon to a class, to colleagues, talking about disambiguation. It's like a philosophy. It's the way we perceive the world and what our goal is within it. And I came later to realize that Wikipedia just uses that word to mean that, yeah, there's some stuff on this page that needs work. But by God, it's still a good word.
That is a great word. That reminds me of, I don't even remember, it was decades ago, but there was some sitcom and I watched an episode of it on an airplane going somewhere. Two of the workers bought their boss a word of the day calendar that they custom made that was all made up words. And then every day she would use one in a sentence.
Well, aren't you the perpipity one?
Two funny things with me in words is, one, I will learn a word that I think I know the meaning and that I like it, and oh my gosh, I am not shy in using it. When Andrea was pregnant, we have twins, we were out shopping for cribs, and for any of you out there who are expecting or have a newborn, as you know, that you obviously don't love your child if you buy the cheaper version of the product. And we're looking at cribs, and you can get this awful death mattress for some expense. But if you love your child, there's this improved mattress. And I said, well, I assume it's inflammable. And the woman looked at me, and there was a long pause, and she said, no, it's not. It's not inflammable. And I said, really? You would think by now that those would be
technology.
And all. And Andrea's like, that's not what inflammable means. And I was like, well, there's flammable and there's inflammable. And it's inflammable turns out to easily bursts into flames. So, this nicer mattress, so it easily bursts into flames, I assume. No, it doesn't. Another one that I have misused repeatedly is nonplussed.
Okay.
So I've used this for years.
Yeah.
In a stressful situation, I am totally nonplussed.
Is that wrong? Oh my God, tell me.
Easily confused, surprised, or stunned.
I thought it just meant unfazed.
Bewildered, confused, easily surprised. Did you not know this?
Oh.
Do you know the number of
This
times
is an excruciating teachable moment. Good thing we're not recording
to
this.
myself as nonplussed?
You keep using the word. I do not think it means what you think it means.
Wow.
But here's where it gets worse. How many times have you been in a situation where someone else has used a word that you don't know what it means, but you're just going to go along for the ride?
Oh, there's that inner dialogue where you're like, oh my God, do I just fess up or do I play it cool? And once you play it cool, you pray you don't get called on this.
Well, so two things. First is you never fess up. Okay. Dude, I'm surprised you even gave that a part in the numbered list. You never fess up.
All right.
And second, I got to tell you from personal experiences, by not fessing up, it just gets worse by the minute as the conversation proceeds.
Oh, yeah.
So that's what brings us to our topic for today. A number of years ago, I don't know how long, I was at a conference and one of my favorite people came up to me in the lobby. There was some Danishes and green hard bananas and bad coffee. And it was Niels Waller from the University of Minnesota. And Niels's name has come up before. Mm-hmm. We were talking about his work with Allie on Haywood cases in EFA. We had a whole episode on that.
That's right. And a great guy.
And a great guy. Niels is funny. He is smart. He is creative. I really, really like Niels. We hadn't seen each other in a year or two, and we do the mandatory, hey, man, how you doing? What are you up to? And I said, oh, are you presenting it later? And he said, yeah, I am. I'm on some recent work I'm doing. I'm, what are you up to? I'm looking at fungible weights. And I was like, oh, really? All right, fungible. All right. Looking back over the tapes, if we were to review them on Monday after the game and the coach slows it down in slow motion and says, all right, you had an opportunity here. And here's what you did.
Drawing an X on
Drawing it
the
out
screen.
and saying, all right, here's the choice you made in this situation. Rest of the team, what else could he have done here? And how would it have changed how the play unfolded? Let's just say that I'm going to be doing laps after practice on this one. I had the opportunity to say, what is fungible? But I'm a male. I'm a faculty member. I'm a Curran. I'm never going to say, I don't know what that means. And I'm like, oh, really? What are you doing with them? Having no idea what the word fungible means. And he goes into this really wonderful description about models and how they're best linear unbiased estimators, but that we need to factor in fungibility and to think about what the implications are. And I'm like, well, you know what I always say, fungible, schmungible. Yeah, obviously, well, who wouldn't think about this?
Am I right or am I right?
And at this point, I'm like, I can't even climb out of the hole that I'm digging. And it's also kind of like where you're on the third date and you don't remember how to pronounce her name, but you're way too far in to clarify that. And so you try something like, how does your mother pronounce your name? And she looks and says, Jane.
You don't know my name, do you?
Yes, I do.
What is it?
Mulva?
So I'm like way in the third date where I've forgotten her name. And so we go back in and he gave a brilliant, wonderful talk where I did figure out what the word fungible actually means. And that's what I want to talk about today is fungibility.
Okay. How do we get into this topic? Do we start with the Merriam-Webster dictionary definition?
That would imply I looked it up at some point over the last 15 years and would know what fungible means. Okay, this is really awkward. I probably should have looked that up before we started recording.
This is Sir David Attenborough. The word of the day is fungibility, the definition of which seems rather important given that today's quantitative episode is built around it. Fungibility is the characteristic of being able to be replaced by another identical, mutually interchangeable item.
Well, the irony is it's more widely understood now because of NFTs. Everybody has heard about non-fungible tokens.
Yeah.
NFT. Wow. Okay, that was an eye roll. Folks, I don't know if you felt the eye roll in the audio, but visually, I'm kind of impressed your eyes came back down out of the back of your skull.
Yeah, I don't even know what to do with that whole topic. It's just weird to me.
I don't have Merriam-Webster's, but it means interchangeable. Mutually interchangeable. One is as good as the other. If two things are fungible, it doesn't matter which one you have. They're exchangeable. They're interchangeable. That's why the source of the definition of non-fungible token is if it's non-fungible, there's only one, and it's not equivalent if it's exchanged.
Non-fungible is unique.
How I had someone describe the non-fungible token to me is it's as if you had a Monet print where the prints are fungible. You go into the museum store and you buy Haystacks at sunset, and the whole stack of the prints are fungible because any one of the prints is exchangeable with the other one, but the original is non-fungible. And I got to tell you, we had an episode, I don't know how long ago, but it was on equivalent models. Remember, these are not alternative models. They're equivalent models. They're models that you rearrange observed variables, you change single-headed arrows to double-headed arrows, you change one-way effects to two-way effects, and they give you the same log likelihood. We figured if that didn't scare the crap out of you as a data analyst, we're going to up the ante.
Oh, yeah.
We're not going to move boxes. We're not going to move arrows. We're going to say, okay, pretty boy, you want your precious little model? Go up and Sharpie it in on the whiteboard for me.
Yeah, we're going to give it to you.
Don't change a thing.
Good for you. You got it right.
Good for you.
What could possibly go wrong?
And your precious little model had an R squared of 0.256. We're going to change that to 0.253, and we're going to show you there are an infinite number of regression coefficients that will give you that R squared. And let's see how you sleep at night now. Thank you, Niels. Like as if Lee and Hirschberger didn't keep us awake at night, Niels now is like, holy crap, your precious little regression coefficients, if we move the R squared 0.001, we now have an infinite number of regression coefficients that will give you exactly that R squared. How you like me now?
How you like me now? How you like me now?
Okay, so that's a lot to take in. How about if we... let's wait for the ground to stop rolling here. Because this feels like there's a worldview about to change.
And that's a really good analogy. People talk about where you have these salient events and it forever changes how you view a prior belief. One is earthquakes, and people will talk about seeing the ground wave like waves on a shore at a beach, and that for the rest of your life, the ground is no longer a stable, solid thing because you saw it surge and wave during an earthquake. I think this is very similar. Those regression coefficients that you get and the standard errors and the confidence intervals are maybe not what you think they are.
Whew.
So Niels is that earthquake. Thanks, buddy. All right, so let's orient before the earthquake. They don't name earthquakes like hurricane. They should. If they named earthquake, this would be the Niels earthquake. All right, so we're going to name that. We're going to name this the Niels earthquake.
Okay.
As Niels points out in his own writing, oh my gosh, he is such a wonderful writer, and it is so engaging.
Terrific.
And even with his most technical stuff, he kind of holds you by the hand walking through it, and you feel like you actually understand it. So well done, but we're still going to name the earthquake after you. Let's pre-earthquake think about a lecture that all of us have either given or have been part of. So we're going to start very simple with a one predictor regression. And we know that ordinary least squares is we want to select the value of a regression coefficient that minimizes the sum of the squared residuals. And the residuals is the difference between what we observed on y and what is predicted in y hat. So y minus y hat is the residual e. We square the residuals e squared. We add them up as the sum of the squared residuals. And we want to pick in a one predictor case that coefficient that gives us the smallest smallest sum of the squared residuals possible. Where you may have either given this as a lecture or been part of it is you go up to the board and you draw an XY axis. And on the x-axis, you put b sub 1 as your regression coefficient. And on the y-axis, you put sigma e squared, which is the sum of the squared residuals. We can do what's called brute forcing it. And we say, well, what if the regression coefficient were 2? And I walk up to the board and I put a little dot on the board and I say, well, here's the sum of the squared residuals that a coefficient of 2 would be. Well, what about -1? And I put another dot. And I say, well, what about 0.5? And I put another dot. And you start to fill in the dots. And if you do it more or less right, it starts to outline a parabola. Actually, a really beautiful parabola. And you say, holy cow, instead of brute forcing it, I wonder if I can write an equation for this. And then you put in this really pretty parabola. It goes down, down, down. There's some bottom and then goes back up, 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 up. And you say, well, I could brute force this, but I remember from high school calc that I can write a derivative for this.
Ooh.
The derivative is the slope of the tangent line at a given point on the curve. And I can say, well, if we're trying to find the bottom of that curve, that is, minimize the sum of the squared residuals, we write out the equations for that derivative and we fix it to 0 because that's where the slope is 0. It's horizontal. In regression land, we call that a normal equation. We solve it and it gives us that point for B1 in which no value gives a smaller sum of squared residuals than that value of B1. And all of us wax poetic about it. Nowhere in this universe or any spider multiverse is there a value of B1 that gives you a smaller sums of squares. That's one predictor. 2 predictors. You have X1, one corner of the room, X2 is the other corner, Y you go up. Remember my plywood and tennis balls from a prior episode? It turns out I know nothing about statistics because I'm going to generalize plywood and tennis balls into an egg.
Okay.
That parabola for one predictor now becomes a 3-dimensional egg. You're trying to feel along the sides of the egg to find the bottom of the egg for what is the joint value of B1 and B2 that together give the smallest sum of the squared residuals. You have 3 predictors? Well, now it's a hyperegg.
A hyperegg is not actually a thing. Patrick just made that up, but it is a lovely notion.
And what all of us have learned is under assumptions, there are no combinations of values for our regression coefficient that will jointly provide a smaller sum of the squared residuals than those OLS estimates.
I love the way that you're describing it. You use the term brute force at the beginning, almost as though you are wandering this egg trying to find that lowest point. The beautiful thing about this in the regression system is that there's actually a closed form solution for that I think you beat people over the head with in the Matrix episode, right?
That's right. We have the function for the minimizing the sum of squares. They're partial derivatives. You take a derivative of that function with respect to each predictor. You get the derivative, you set those to 0, and you solve, and that is the bottom of the hyperegg.
X prime X inverse X prime Y.
There you go.
There you go.
That saves you the trouble of doing the derivatives. One thing about moving to the fungibility is there is a breathtakingly beautiful geometry to it. So I did tennis balls, plywood, and a hyperegg in the Spiderverse. Can you maybe formalize that a little bit with the geometry before we start talking about earthquake kneels?
I'm going to harken back to something that I talked about in the last episode that we had, the Matrix Part 2. As we described in that episode, every variable that we have can be thought of as a vector in space, a space that's defined by the dimensions of all n people or n cases that we have. So there's a vector that goes out for x1, there's a vector that goes out for x2, and we're going to stick with those for right now. And the goal is to try to understand the relation that they have with y. And as Patrick just talked you through, what he was looking for was combinations, this cocktail of x1 and x2, a linear cocktail, where we have some weight that goes with x1, some weight that goes with x2, and we're trying to build something out of those that gets as close to y as possible. And we call that thing y hat. In the geometric world that I described previously, we have this vector x1 and this vector x2, and they might be very close to each other if they correlate highly. They might be closer to right angles if they're more orthogonal or uncorrelated with each other. And then we have this y vector. The way that we described it in that episode was, think about x1 and x2, those two vectors, as defining a plane or a tabletop. And that plane or tabletop represents all possible linear combinations of x1 and x2. And the y vector as being a vector that sticks out of that particular tabletop. Y has an infinite number of shadows on that plane that's made by x1 and x2. If you were holding a flashlight above Y and moving your hand all over the place, you would get these shadows in that plane made by x1 and x2. There's only one shadow that is as close to that y as possible, and that's the shadow directly beneath it. So when Patrick wanders the space, sort of metaphorically saying, how much x1 do I need? How much x2 do I need? What he is doing is arriving at that place that is the perfect straight down, perpendicular projected shadow of y into the plane defined by x1 and x2. And that is a linear combination of x1 and x2 with weights that are exactly the same as Patrick described. One last reminder about that is that once we have identified where that perfect shadow of y is, that y hat, we can measure the angle between the actual y and the y hat. And the angle between those, if we take the cosine of that, becomes the multiple correlation, big R. That big R is as good as it's going to get, right? Of all the linear combinations of x1 and x2 you could build, that is the one that has the highest correlation with the actual y. But of course, there are other shadows that might have slightly lower values of R, slightly bigger angles with that actual y, and we're going to talk about those.
It truly is a remarkable characteristic of ordinary least squares regression that there exist no set of regression coefficients that lead to a smaller sum of the squared residuals. Mm-hmm. If you go a billionth of a point to the right or the left on that hyper egg, the R square will get smaller. Mm-hmm. There is no combination of coefficients that give a smaller sum of the squared residuals, but holy crap, there are a boatload of them that give almost the smallest sum of the squared residuals, but may lead us to write a different discussion section.
Oof.
That's where the word fungible comes in. And this is where Niels trots out on the field with his 2008 Psychometrica paper. A fungible weight is one that can be exchanged with another, but has no difference in the impact on some outcome that we described. That's the fungibility. So what does that mean? Well, let's say that we take our multiple R squared that we have, and I'll just make up a number, and it's 0.25. Now, it is true that there is no combination of our predictors that will give more than an R squared of 0.25. But what if we make it trivially lower? Mm-hmm. Let's say what we obtained was 0.25, and we say, all right, well, what about 0.245?
That's close.
What's 5/1000th of a point between state university employees? Mm-hmm. The difference between 0.25 and 0.245. Trivial difference. Niels proved that for a model with 3 or more predictors, there are now an infinite number of regression weights that will result in an R squared of 0.245. The pictures on your wall are starting to jiggle. An infinite number of regression coefficients, might I say fungible regression coefficients, that all lead to 0.245. And here's the drunken punch in the face. That's 5/1000ths of a point in multiple R squared, but some of these may combine where you would write a different discussion section for your model results.
Even though the R squared is only 5/1000ths off, the ground is so unstable. When I talked about there being this one perfect shadow underneath Y, and that its angle conveys information about the multiple correlation. I also said there were a number of other shadows if we moved our flashlight. If we didn't hold our flashlight directly above Y, but moved it a little bit to the side, we would get different shadows that have different angles with the Y vector. Every one of those shadows represents a different linear combination of x1 and x2. If Patrick says that he wants something with a squared multiple correlation of 0.245 rather than 0.25, it would come up with a correlation that is lower. What that means in terms of projections is that Y would make an angle with such a thing that is actually larger, right? That is slightly suboptimum. In this space that we're talking about right now, where we have two variables, x1 and x2, defining the tabletop, defining the plane, if Patrick says, yeah, I don't want that perfect angle, I want something that's just a little bit bigger, the answer is, well, there's something that's just a little bit bigger off to the left, and there's something a little bit bigger off to the right. I can move my flashlight left or right to create that perfect shadow that makes the angle with the correlation that Patrick describes, and there are two of them. And that's it in the world with only two predictors. That to me is already ground shaking. That you tell me, wait a minute. The correlation is off by a tiny bit and now there are two solutions. Not only are there two solutions, they can be very different from each other, right? Because one of them veers off to the left of the perfect shadow of Y, one of them veers off to the right. And those themselves can be quite different from each other, meaning that they're very different in terms of the slopes. And so they're potentially, as Patrick said, very different in terms of shaping your discussion. Now, if you move that up to three or more predictors, there isn't just a shadow to the left or a shadow to the right. There are shadows in multiple dimensions. And there are lovely explanations that involve ellipsoids and other completely made up words. But the idea then is, as Patrick said, you get an infinite number of regression weights, all of which yield the exact same R squared. And even if it is a tiny bit suboptimal, they can be very different.
And they're not always very different.
That's right.
This is actually a measure of model sensitivity. It's almost like a diagnostic. Okay, you have your magical vector of OLS regression coefficients under a glass dome on your desk. Well, how sensitive are those to 5/1000th of a point in R squared terms?
And I think there's something we need to be very clear here in distinguishing. This is not sampling variability.
Oh, right? And it's so hard to get your head around that.
That's right. When you find that optimum spot, when you're doing OLS regression or other things as well, when you find that optimum spot, that's optimum for the sample that you have. And if you get another sample, then you will find optimum for that sample and then optimum for the next. So upon repeated sampling, there is natural variability that you would expect in the slopes that we're talking about. And as you got bigger and bigger and bigger samples, you would expect that natural variability to get tighter and tighter and tighter, so that you don't expect there to be a whole lot of uncertainty in the slope estimates based on random sampling variability. This does not have to do with that. Go ahead and imagine that you have got giant samples. So you've got these tight little confidence intervals around your slope estimates. Go ahead. Let's get that out of the way. What Patrick is talking about is uncertainty on top of that is due to this fungibility issue.
There are a lot of really nice recent papers on this, and some we'll comment on here. If we don't comment on one, it doesn't mean anything other than we just didn't comment on one. But we'll put a long list in the show notes. But in the last 3, 4, 5 years, there's been a burst of really interesting work. And related to what Greg just described, Jolynn Peck has a really nice paper where she talks about the very issue that you described, and she differentiates fungible parameter estimates, and she distinguishes that from what she calls confidence sets. And those are confidence intervals and confidence regions on the parameter estimates themselves. So what that means is you can have a large sample size, you can have a small standard error, you can have tight confidence intervals, you can have a well-fitting model. Do you know what the statistical phrase is of how that links to what we're talking about with fungibility? It don't matter. you can get these differences in interpretation at 5/1000th of a difference in R squared because this is operating in a different part of the model. I don't care if you have a large R squared and a large sample size. That is not the governing force at work here.
There's this term that you have mentioned explicitly, and it really is a theme of where we're going with all of this, and that is sensitivity analysis. We talk about sensitivity analysis. We use that expression to describe a lot of things, but it usually takes a different form. We might say something like, well, would your results have been different if the distributions of your variables had been different, or if you had left out one of your predictors, or if you hadn't categorized that variable, or et cetera, et cetera, et cetera. So we talk about sensitivity as this robustness to different changes that we might make in the circumstances and see whether or not the ultimate inference that we make stays the same or doesn't. This is in that family, but it is just so potentially, not necessarily, dire in terms of its consequences, and I think we have no awareness of that. So can you talk about this in terms of sensitivity analysis and how it can be helpful for us?
Well, I didn't want to interrupt and correct you, as I think it's less sensitivity analysis and more poke and stick.
Okay.
Right? Because we've talked about that a lot, and we've gotten yelled at on Twitter a lot about this poke and stick thing. You're exactly right. We do our sampling, we do our measuring, we do our modeling, and we get a final model that we want to believe in. And then we pull out our poke and stick, and maybe we add an interaction or a curvilinear term, or maybe we do a nonlinear power transformation. Maybe we add a couple of nuisance parameters that moderately improve fit and see what the effects are. Maybe we omit a variable. So we have regression diagnostics, and you do studentized residuals, and you look at outliers, and you look at DF fits and DF betas and all of these things. And the point is, you kind of slap the model around and see, well, how stable are my results in how I would write my discussion section. That's how I often think about it. Mm-hmm. Sure, things are going to change here or there, but how would I change my discussion section? And if you can jab at it with the poke and stick and you don't get bit or stung, then you have some confidence in it. This is a similar kind of thing, but we're approaching it from a different angle. The logical syllogism is pretty straightforward. You fit an OLS regression and you get your R squared. You subjectively pick a trivially different R squared. Mm-hmm. And then you find all the regression coefficients that would give you that trivially different R squared. Now, with 3 or more predictors, there are an infinite number of those, and so there are different strategies for picking candidate values. Niels has another paper where they derive the maximal difference between regression coefficients, which is kind of cool, right? Is how far apart can those be?
Oh, that's just crazy scary.
Yeah, well, that is where we move from the picture frames rattling to the ground is now waving and liquefying. Thank you, Niels. But you can derive those, and then that becomes a measure of sensitivity, not sensitivity to outliers, not sensitivity to an omitted parameter, but how sensitive are your parameter estimates to where this global minima resides versus being really, really close to that global minima to the point that nobody cares.
Right.
There's the famous Howard Weiner line of it don't make no never mind.
That's right.
Right? Is okay. Move 0.005. Nobody gives a crap. But oh my God, Earthquake Niels shows us that one of your precious predictors is positive and significant with an R squared of 0.25 and is negative and significant at an R squared of 0.245. Go ahead and hang that big heavy picture over your bed and have a nice night's sleep.
So there's an old expression, a difference isn't a difference unless it makes a difference. We can talk about a difference in terms of R squared here of being whether it's 5,000ths or 0.01 or whatever. Heck, difference in R squared of 0.01 is nothing. It is nothing in the grand scheme of our lives. But as Patrick is saying, it can make a vast difference in terms of the weights that we have right now. That is where the earth rattles, because ultimately our goal is to understand how things work. And it's one thing if our only only goal is to know whether or not a variable is a statistically significant predictor. But that really shouldn't be our end goal, right? Our end goal should be to understand the magnitude of the relations here. In the end, we might find that, oh yeah, the same things are statistically significant. That's great. That just means you probably had enough power still. But the values that are associated with them can lead to fundamentally different assessments. It can lead you to conclude that one variable is much more important in understanding why than the other, whereas the opposite might be completely true. This is really getting at the core of generalizability and understanding how systems function and replicability, and all of this still remains scary as hell to me.
So everything we've been talking about, just to get our head around the problem and also to stay consistent with Niels's initial work, was in linear regression.
Right.
We have a single dependent variable. We have a multiple R squared. There's a follow-up paper that Niels did with a colleague of his, and it's Jones and Waller that was in Psych Methods in 2016, and that generalizes that to logistic regression. And logistic regression, of course, is a regression model for a discrete dependent variable, but we still only have one dependent variable. And they address some complexities in the logistic that we won't belabor here. A whole lot of us say, yeah, I mean, regression is nice, but I've got an SEM. I've got a path model. I've got multiple indicator latent factors. You've got an R squared, but now if I have 4 dependent variables, well, I have 4 R squareds. There's one for each dependent variable. What do you do with that?
Right. First of all, you pay less attention to the R squareds, right? If we think about a larger measured variable path model or confirmatory factor model or latent variable path model or general structural equation model, however you want to call it, and all of the other extensions as well, the growth modeling things that you and I tend to like a lot, we don't tend to gauge the worth of those models by the R squareds associated with every endogenous variable, every dependent variable that we have in the system. Maybe we should pay more attention to that, right? If we listen to some of the things that Doug Steinley had to say a couple of episodes ago.
I feel like if we just were to boil it down to regular regression, if we get significant predictors in regression, it's going to be related to like a significant F-test for the model. And that means that we're minimizing the mean squared error to some degree, which is also exactly what a good prediction is, right? A good prediction is going to be minimizing the distance from the predicted point to the observed point. So you're going to be minimizing the same residual. And I feel like, tell me a model that you think is a really good model, building on theory, but it can't do a prediction. Why is it a good model? That's really hard for me, just from a practical point of view. It's like somebody presented and say, hey, I got this new model. And I'm like, what can it predict? I'm like, nah, nothing really, but these things are significant. I'm like, is it a good model?
But in the structural equation modeling world, there was a decision made a long time ago to move from an R squared way of thinking about the value of a model to something that was more global. There are a variety of indices, as we've talked about before. We had a whole episode first season, but one of the ones that has been around for a while and doesn't seem to have any signs of going anywhere is the root mean square error of approximation, Steiger and Lynn's RMSEA. It is a measure that combines an assessment of the fit of the model overall, the absolute fit in the form of the model chi-square, if you want to think about that, or really the model fit function. It has sample size involved in it. It has degrees of freedom involved in it. And by virtue of its inclusion of degrees of freedom, there's an element of parsimonious correction that is tied to it as well. Well, some of the wonderful work that followed from Waller by Tae-Hun Lee, Bud McCallum, and Michael Brown extended these ideas of Waller's into the structural equation modeling world, where it's not just a family of regression coefficients that you have, it's actually all the parameters in your model. We have this fit function, and we are trying to minimize this fit function, which simultaneously maps on to maximizing the likelihood associated with our data. Well, one way to measure how well we've done that is this root mean square error of approximation. And let's imagine it came out to be 0.04, and we say, that's a pretty good RMSEA. In fact, that's the best RMSEA we could possibly get with these data. Well, what Lee, McCallum, and Brown said, what if it's not 0.04? What if it's 0.043? Would you lose sleep over that? And the answer is, heck no, I wouldn't lose any sleep over that. I'd be pretty much just as happy with an RMSEA of 0.043 as I would with 0.04. And what they showed, which is the extension of Waller's work, is that it can, not necessarily, but it can make a world of difference to the parameters that are in your model, the parameters that you are using to try to understand a complex system. And Earthquake Waller just had repercussions on the other side of the globe.
I so strongly recommend looking at this paper. I've actually got a copy right here in front of me. It's 2018 Psych Methods. Again, if you're somebody looking for an area of research that is moving quickly and there's lots of good work yet to be done, this issue of fungibility across a whole array of types of things that we do, there's a lot of really interesting things to be done. All right, so this is 2018, so we're not talking about stuff from the 90s. This is pretty rapidly moving. If you're looking for a new gig, there's some pretty cool stuff to be done here. But it's wonderfully written. It is very, very clear. Tae-Hoon is a wonderful guy. He was here at Carolina. He got his PhD under Bud McCallum. He and I worked together quite a bit, and he's just a lovely, lovely guy. He's at Chung-Ang University in Korea. They have some figures and plots in there that do a really nice job of laying out what we tried to describe earlier about how you have a parameter on one axis, a parameter on the other axis. Now, the maximum likelihood estimates are a point on that plot, but they're not closed form anymore. So you alluded to this earlier in the conversation, is that one of the beauties of OLS is as long as you have one observation more than the number of predictors, you will always get a solution in OLS. Now, it might be a horrible bad solution. Well, in an SEM, we're very often in a situation where there aren't closed form, and so we get maximum likelihood estimates. So I'm looking at their figure 1, and in the maximum likelihood estimate, you get that joint pairing of what they refer to as theta 1 and theta 2 as the two parameters, and there's a single dot that represents that vector. Well, then in the next panel, as you described, they move a vector out, some degree of misfit that we're willing to tolerate. And so an RMSEA that differs by 0.005, who cares? Nobody cares. Then you can paint the boundary of an ellipse where anywhere along there, that pairing of coefficients gives you exactly the same RMSEA. And then their final plot is really cool, is drawing on Niels's work of deriving the maximal distance, is you can actually get the endpoints of that primary axis on the ellipse and say, holy crap, we can be way over here on the ellipse, we can be way over on this other side of the ellipse, and it gives you exactly the same RMSEA. Now, what is the complication in the SEM? Because you don't have closed form, these ellipses and hyperellipses start getting really complicated. They have an example that they use that has 67 free parameters. They do two things. One is they focus on a small number of ones that are of primary theoretical importance and consider the other nuisance. And second, they brute force it. And what that means is they write code to plow through tens and hundreds of thousands of different values that you can get, and then they have a way of graphically demonstrating that and trying to identify this in a real data analysis. So it's really, really cool. Is everything you think about that SEM, we can just scale that up as another measure of sensitivity. There is a really cool paper that's co-authored by a colleague of yours, Jeff Herring. And again, 2019. Come on, folks. If you're looking for a dissertation, if you're looking to contribute, oh my gosh, there's so much interesting work to be done here. But Prendez and Herring in SEM, the journal, Measuring Parameter Uncertainty by Identifying Fungible Estimates in SEM, they have a wrapper package for Levon and R that tries to quantify this.
I think it's very clever what they did, because the work by Lee, McCallum, and Brown admitted that the mathematics of identifying this whole collection of fungible parameter estimates is really, really formidable. And they even said that what they have is important but kind of clunky for the user. So along come Prendez and Herring, and what they said essentially is, you have already wandered that space. You have already wandered that mountain in the iteration process that has already occurred. On your way to that optimum RMSEA for your sample, you have hit suboptimum RMSEAs. So what happens at those suboptimum RMSEAs? we don't usually see any record of that, right? All we get is where we are at the last iteration. The only time we see parameter estimates at some suboptimum RMSEA is when our model fails to converge and the output says, well, here's where you left off. You might want to pick up from here if you're going to iterate some more. That's about the only time we see that. And what Prendes and Herring said is, well, maybe we can find a way to collect that information throughout the iterative process. And then once we have that, we can know what the parameter sets are at these different altitudes of our fit function. If you go stand on the top of the mountain, you are in one location. Let's say that mountain is 14,000 feet. There you are. If someone says, go down to 13,900 feet. Well, you go, what do you mean? Where? I could go down this way, this way, this way, this way, and be on very different sides of the mountain. What Prendes and Herring did is they said, well, yeah, and you just walked that whole mountain all over it. Let's take that information and give you a sense of what those parameter estimates would be. And I thought it was terrific that they created that package. It's called PS Index, PSINDEX. And as you said, it goes right along with Lavon, and it can provide that information for you along with your optimum parameter estimates. And I think that's exactly what we need to be doing. Not just sounding the alarm, right? Not just cursing the darkness out there, but actually putting things in the hands of users so they can understand, in the end, is this going to substantively alter the inferences I'm going to make? Or do I have more confidence in the claims that I'm going to make about the relations that I'm studying in this larger model?
I love your description of the mountain, and it reminds me of something that happened with my wife and me 26 years ago. Mm-hmm. We went to Steamboat Springs in Colorado for our honeymoon. We were out on the first night after our wedding. It was a cold night, high in the Rockies. And we were out on a walk, and the full moon was just peeking up behind the mountain. Oh, and we cuddled up. It was cold. We sat there and we watched the full moon rise, and it was glorious. We drove back to our cabin, got out of the car, and the full moon was just peeking up behind the mountain. And we were both like, screw this. We're going inside. Right? It's like it's relative. You go down a little bit on one side, you go down a little bit on the other side. This really is a form of poke and stick. Mm-hmm. We have really well-developed diagnostics and outliers and DF fits and DF betas and modification indices, and we have cross-validation indexes, and we have a whole focus now on reproducibility and replicability. This is not histrionic, hyperbolic, your model is crap. It doesn't mean anything, because a number of these published applications reanalyze prior models and show that you can mess around with these criterion and they're really stable in the conclusions that you would draw. Well, that's great. Yeah. That's a really good thing to find about your model. But they have other examples where you change these criterion by just a little bit, and you would change your discussion section. In that sense of you need to be aware, right? Doug Steinley, when he was on the microphone that was an old tomato soup can and a string in the bottom of a dumpster in Columbia, Missouri, he talked about two things that are related here. We should start with eigenvalues and eigenvectors of our data matrix, no matter what we're doing, just to orient to the data. And a couple of pages into Niels's first 2008 paper, there sit eigenvalues and eigenvectors. These play a critical role in this. The other thing Doug groused a lot about was the difference between prediction and explanation. That kind of relates here as well, as we reify these parameters that we get, right? They are the truth as God sees it. And it's our own fault because we say there are no other collection of values that give you a smaller sum of the squared residuals.
That's right.
But the second half of the sentence we leave off is, but there are an infinite number that give us a sum of the squared residuals that are trivially different from this one and nobody would would care about. See you on Tuesday. Be sure to get the problem set into me by 9 o'clock. So what are some take-home points here? First, I've been saying Earthquake Niels, and you said Earthquake Waller.
Oh, did I?
You did, but it rolls off the tongue better. Earthquake Niels has a harder transition, so we're going to go with Earthquake Waller.
Okay.
It rolls off the tongue. So what are the implications of Earthquake Waller? Well, one is let's not quite brag so much about those final estimates we have. Because yes, those are final estimates that meet some criterion that we have defined, but holy cow, there are a whole bunch out there, and by whole bunch, I mean an infinite number that are damn near exchangeable with those.
Yeah.
And we need to be aware they exist.
You can't unsee this. You can't unhear this. Once you're aware of this particular problem, I think it will start to become your responsibility to understand the extent to which this is going to influence the inferences that you have. Ultimately, I'd like to see this as standard kind of output associated with any modeling package, quite frankly. But until that time, I would really encourage researchers out there to hold their breath, go in and request that kind of information so that in the end, on the one hand, it might lead to tremendous instability and uncertainty regarding what you can conclude regarding particular predictors or the role that variables play in some larger system. On the other hand, it might actually bolster your ability to make claims, and how nice that would be as well. So I think this is moving from this curious thing that some nerds sort of figured out to something that is going to be shifted as a burden of responsibility on the researcher.
And it needs to be supported, right? I don't want to get into the rabbit warren about how we're anti-pre-registration. We're not. We're not anti-pre-registration. What we were talking was paying attention to your data and the sensitivity of your models to your results and feeling comfortable navigating those waters in trying to understand the extent to which your model is sensitive to characteristics of the data, characteristics of the parameterization, and now characteristics to the sensitivity of your parameter estimates. This is information to have. Now, what to do with that? That's a harder question. Many of us have taught regression diagnostics, and maybe you have an example where there's an effect that's significant in the presence of the full sample, but it goes to non-significant if you drop 2 observations. And then people say, but what do you do? What do you do? You shrug and say, I don't know, right? You've got to make an informed decision. You've got to convey that to the reader. We have to turn toward replication. What do you do if you do these kinds of things and you find that your parameters are not sensitive in this way? Well, that's good. As Greg said, that's really important to know.
Yep.
What if you do this and you find out, holy cow, if I give up 0.002 on my RMSEA, but my core predictor goes from significant to non-significant in a large proportion of the fungible estimates, that's something you need to communicate to the reader. It doesn't mean that your predictor is not salient and important, but it means it's unstable. We need to know this when we're interpreting the results.
Man's got to know his limitations.
Especially as we continue to build a replicable science.
And on that last point, thinking about each study being this pebble in the pile of science, that each study is a data point, and when we tend to approach these things meta-analytically and aggregating stuff across all of these different studies, it would seem to be so informative if we had this kind of information along the way also to get a sense of how much weight to attribute to each of these estimates that comes out.
So maybe as a final point, as reiterating what's come up a couple of times is, oh my gosh, there is so much interesting work to be done here. If you go back to Neil's original work, he has a couple of follow-ups, some collaborative work with Jeff Jones. If you read Tae Hun's paper, read some by Jolyn Peck, by Jordan Yi Prendes, and Jeff Herring. Go orient to these papers, and there's just half a dozen things that fall out of work that has yet to be done that would have a very high impact. As Greg just alluded to, this should be part of standard output from an SEM package. What would that look like? What are criteria we would use? What are measures that might indicate a problem versus not a problem? How could we make this part of reporting standards? There's a lot of work yet to be done on this.
You sounded really excited talking about that topic.
This is cool.
It is very cool. I would say that you were gruntled.
You're making up words again.
Nope. If there exists disgruntled, then today you are completely gruntled. And I appreciated that.
Then I am gruntled and nonplussed. If you can learn a word from Wikipedia, I can learn a word from R. You are officially deprecated.
Did you say defecated?
Thanks, everybody.
All right.
Bye-bye.
Bye. Thanks so much for joining us. Don't forget to tell your friends to subscribe to us on Apple Podcasts, Spotify, or wherever they go to learn new words or new definitions for words they already had perfectly good definitions for. You can also follow us on Twitter, where we are at QuantitudePod, and visit our totally redone website, quantitudepod.org, where you can leave us a message, find organized playlists and show notes, listen to past episodes, get transcripts of recent episodes, and other fun stuff. And finally, you can get amazing Quantitude merch, like shirts, mugs, and notepads, from redbubble.com, where all proceeds go to donorschoose.org to help support low-income schools. You've been listening to Quantitude, the podcast that listener Caleb Ching of Cincinnati, Ohio said makes his 7-mile run feel like a 10-mile run. Today's episode is sponsored by statistical terms that don't exist, but really should. A model may be recursive or non-recursive, but how about a model that is just plain cursive? It looks quite lovely, but its estimation leaves you cursing ever even starting the research project in the first place. A cursive model. And correlation matrices might be positive definite or non-positive definite. How about a positive non-definite correlation matrix? When you have correlations above 1, below -1, or just that make no damn sense at all. A positive non-definite correlation matrix. And finally, for missing data, there's MCAR, MAR, and MNAR. There should also be MWTF, missing what the fuck, when you really have no fucking idea why data are missing. MWTF, missing data. We highly encourage you to integrate these terms into your daily statistical lexicon. This is most positive non-definitely, not NPR.
Gregory, you are inflammable and a bit perpitty.